Hello and welcome to today's webinar. My name is Tyler Reid. I'm the Manufacturing Applications Manager here at GoEngineer. And today we're going to be talking about CAMWorks and specifically some high-speed machining strategies within CAMWorks. We're going to focus on high-speed machining strategies within CAMWorks specifically, but I wanted to talk a little bit about high-speed machining just in general. High-speed machining is one of those phrases that we hear all the time in machining these days, and it really doesn't have a set definition. A lot of people judge it by the material removal rate, or they judge it by the spindle. I've heard some people say you can't do high-speed machining unless your spindle speed is 18K or higher. Other people go by the feed rate. 500, 600 inch per minute feed rate is high-speed machining. And I've also heard from other people that it's based on the machine, and high-speed machining is essentially machining at the highest speed or the most efficient speed based on the machine build and the spindle and all that. My personal definition is probably the material removal rate. If you are doing, 3 to 4 to 5 times the removal rate over conventional machining, then I would consider that high-speed machining. One thing that everybody agrees upon is that higher spindle speeds enable higher speed machining, and they do that through reducing the heat that's generated during machining. It's a little bit counterintuitive, but as spindle speed goes up, heat in the process actually goes down. And how much it drops is actually different based on the material you're cutting from. Aluminum has the most drastic drop, whereas say a mild carbon steel has the least drastic drop, and then you have materials in between those. Because it has reduced speed, you also have reduced cutting forces, and with reduced cutting forces, that gives you some breathing room to maybe take deeper cuts or move through the material a little bit faster. So some of the techniques that people use, preference is kind of given to smaller tools, especially once you get to some of these high-speed machining tool path shapes. These shapes need room to breathe within the pockets or the slots that they're cutting, and so you can go with a smaller tool. The number of flutes matters. Essentially, the more flutes, the faster the feed rate for a given chip load. And a standard flute number for aluminum might be 2 flutes, and for steels you might be looking at 4 flutes. Once you start looking at high-speed tool path options, you want to bump that up a flute or 2. So with aluminum, we're probably looking at 3 flutes would be ideal. And with steel, probably 5 or even 7 flutes might be ideal for these high-speed machining options. You don't want too many flutes because we are going to be pushing these tools a little bit harder, and with more flutes, you have a weaker core on your tool. Also, you have chip clearance issues and heat issues as well. So you don't want too many flutes, but you're definitely going to have more flutes than over a conventional tool path. High-speed techniques typically do a narrower cut width and an increased cut depth. So we're going to be taking advantage of more of the flute length and less of the flute diameter. So we're going to be able to do deeper passes. And so for materials or pockets that would typically take 2 or 3 or more passes, we might be doing the roughing within a single pass. One thing we do have to be concerned about is tool deflection. As we start to move these tools faster, they're going to be more susceptible to chatter based on the deflection. A lot of tool path calculators these days will calculate or estimate tool deflection based on your stick out and the tool properties and your cutting parameters. And from what I've read, you really want to stay under 3 thousandths tool deflection, especially at these higher speeds. 1 to 2 to 3 thousandths is probably okay. But once you start, having significant tool deflection at 12, 15, 18,000 RPM, you're going to start to get chatter. Chatter affects your tool life. It affects your tool finish, but that's probably not our primary concern because most of these high-speed techniques are roughing techniques. And especially within CAMWorks, you're going to be using the high-speed technology for roughing and then follow that up with a finish pass. Last thing here before we jump into the CAMWorks specific, as far as toolpath shape, it's going to be significantly different than your conventional toolpath shapes. You have several different toolpath shapes or technologies that create different shapes. One that comes up often is called trochoidal milling. That's not what we use in CAMWorks. We use something called VoluMill. VoluMill is a company that was it's been around for about 10 years, and their primary business is developing toolpath technology. They write code that is then licensed to several different CAM packages, and CAMWorks is one of those. The purpose of VoluMill is to maintain constant tool engagement angle. What that means is that when we target a set radial depth of cut, we're going to try to take that radial depth of cut constantly throughout the entire feature. We're going to avoid corners. As soon as you get into a corner, you might jump from 20 to 30% radial depth of cut up to 90 or 100% full slot cutting. And that's hard on the tool and it's hard on the machine. And what it forces the machinists to do is actually create a buffer in their feeds and speeds. They have to create a safety buffer. So they can't push their machine as far as it can go. They can't push it as hard as it can push because they have to buffer it for these shock zones. And by eliminating those shock zones, by eliminating corners, we can get the most out of the machine. One important aspect of this is that VoluMill not only avoids corners, but it does not create new corners in the process of cutting a feature. So just some quick stats from VoluMill. These come directly from VoluMill, and we do see these types of numbers within our customer base. You're going to be able to increase your machine capacity because your times to cut features, your cycle times are going to be cut in half or even more. You're going to be able to cut more parts. You're going to be able to push a lot more metal through your machine. So it's effectively, maybe doubling the capacity of your machine in some cases. You're also going to save on tooling costs. You're going to save it in two ways. One, your tooling life is going to increase drastically because we are avoiding those shock loads to your tools. They're going to last. They're not going to fatigue over time. You're also going to be able to maybe use carbide tools over some more expensive insert tools. Okay, so you're not going to have to invest so much into specialized, expensive tooling. We can get by with basic, sharp carbide tools or even high-speed steel tools. And this is one thing, this last point I really want to stress is that you do not need a high-speed spindle to take advantage of VoluMill. VoluMill makes your machine more efficient no matter what its capabilities are. By moving the tool more efficiently and more intelligently through the features, it's going to increase your tool life. It's going to increase your cutting time, no matter if you have a 12,000 RPM spindle or you can only spin it at 4,000 RPM. Or if you have machine travel limits, you can't cut over 80 inches a minute and you can't take these 500, 600 inch per minute cuts, that's fine as well. You're still going to be better off. And your machine is going to require less maintenance. It's not going to break down as quickly. I am going to be using a secondary program here, or I should say I did use a secondary program here to come up with the recommended feeds and speeds for VoluMill. This is called the Milling Advisor. It's a standalone piece of software that has actually been discontinued. It's now integrated into CAMWorks 2017, but there are a couple bugs in it I noticed. So I still had this around, and I uploaded it. If you want to download this and kind of go through some of your typical cuts, some of your typical parts, it gives you both a conservative and an aggressive set of feeds and speeds based on a lot of different parameters. And this is just in general in VoluMill, it's taken into account the material you're cutting, the hardness of that material, your tool diameter and number of flutes, and any coating it might have, your tool length. It also takes into account your part holding, your machine taper, and your max RPM and your max inch per minute on your machine. Okay, so it takes all of those into account, and then it has some suggested feeds and speeds. So go ahead and download that if you'd like. It's going to be uploaded there for quite a while. I don't know of anywhere else you can download it. Okay, so we're going to jump into the software, and I'm just going to go over 3 examples quick. We're going to be talking about conventional toolpath shapes versus VoluMill shapes. We're going to be looking at some feeds and speeds data, and we're going to be looking at some cycle times as well. So within CAMWorks, VoluMill is an optional module. It is something that there is an additional cost to. It's not significant, and I definitely think it's justified if you're going to use this portion of the software, because the savings in terms of your machine capacity and your tool life will more than make up the cost very quickly. That being said, if you do not have the module, you can still generate VoluMill toolpath. You can still input feeds and speeds and do some testing and look at cycle times, and you can determine for yourself, based on your parts and the features that you typically cut, is it going to be worth it for you? The only thing the module does is once you have a license, it allows you to post G-code. Okay, so you can create these toolpaths. Everything I show you, you will be able to do on your own. Also, as we go through this, if you have some suggested feeds and speeds, you want me to run through the numbers, you can. I'll admit, I'm not an expert on feeds and speeds. I usually use a calculator myself, and I know everybody has their own idea for what a feed and speed should be based on their experience, based on the machines that they're used to running. And so, take all of these numbers with a grain of salt. The point I want to get across here is that we are definitely going to have more efficient toolpath and greatly reduced cycle times. Okay. So I have a simple part here, a little hourglass shape with a slot on each side. I programmed each side separately. We have a rough mill on the left side using a conventional pocket out toolpath. And these are the type of movements that we're trying to avoid. These corners. Let me look at it dead on. These corners here. As the tool is moving along and speeding through at a certain inch per minute, when it approaches this corner, the machine has to decelerate, completely stop, and then reaccelerate. Also, while it's doing that, the loads on the tool are changing. And the heat is going up, it's going down. It's tough on the tool, it's going to fatigue, it's tough on the machine, the bearings, the ways, all of that stuff. And because of that, we can only run this at, maybe 40 to 60, 70 inches per minute in aluminum. And what I've programmed this at, if we take a look at the tool, we're using a 3/4 inch carbide 4-flute end mill in this case. This is a aluminum 6061 T6. I have this set at 7,000 RPM at about 65 inches a minute. That is a surface feet per minute of about almost 1,400 and a feed per tooth of about 2,500. Okay. Within the roughing parameters, you can see that our cut depth is 50% of the tool, so we're about 3/8 cut depth. And our step over is 60% of the tool. So all of those numbers together, I think this is a pretty aggressive cut. This is a 1-inch deep pocket. And based on our cut depth, we have to take 3 passes. Okay. We are ramping between cut depths. and I have the ramp set at 100% feed rate. Okay. I should say this part is 10 inches long, and the total length of the part, the total width of the part is about 8 inches. So that gives you a little bit of scale. And if I open up the tool, you can see this is a 3/4 inch end mill. You can kind of see the scale of the feature. Okay. Cycle time on this is about 4.5 minutes. Okay, 4.5 minutes. With the VoluMill, let's take a top look at this. Notice we have no corners at all. There, at no point is the tool coming to a complete stop. Okay, every corner is rounded by a certain radius. Also notice we're doing one depth of cut. Okay, so that right away, we're going to have a lot less tool path length. We're using the same tool, that 3/4 inch carbide 4-flute end mill. The feeds and speeds are a little bit different. Now I bumped this up to 12,000 RPM, okay? And the feed rate is 550 inches a minute, which sounds outrageous, but this is actually below the conservative estimate given within the VoluMill feeds and speeds calculator. Notice the inch per tooth is higher. You know, the inch per tooth can be up over 10 thousandths inch per tooth. This is new. If you're an existing CAMWorks user, this button is new. So this actually opens up the VoluMill Technology Expert. So this is the integrated version of the Milling Advisor. Okay, so you see a lot of the same drop downs. We have our material. Okay, when I set the stock material, this gets auto-loaded. You have a hardness, 95 hardness for the 6061. Coating, I'm using uncoated tool. My part holding, I have it set to best. Some options are basically poor, better, best. So that's a little bit subjective. Machine taper is 40. It has built-in 30, 40, 50, and HSK. And the holder type I have set to end mill holder. There's ER collets, there's TG collets, there's hydraulic fixtures, and shrink fit holders as well. Ideally, all of these would affect the tool paths. Now, I'm in CAMWorks 2017 SP0, and some of these are not affecting the suggestion. So I actually reported that as a bug yesterday, and it was confirmed to be a bug. So for that reason, I have been using the Milling Advisor, which is a standalone product. If you look at them side by side, they're essentially the exact same thing. The only extra data that it's asking for me is the tool data. Whereas in the integrated version, it pulls the tool data from the tool being used, okay? So if we look at this, we have a 3/4 inch end mill. This is actually a 4-flute. The length of cut is going to be 1 inch, which is greater than 1.25 times the diameter. Uncoated end mill. Part holding I set as best. Machine taper is 40. End mill holder. Max RPM on my machine I have set at 12,000, and my inch per minute, maximum inch per minute I want to use is 600. Okay, so that's going to vary based on your machine. Then it gives me a conservative and aggressive suggestions. On the conservative side, it's going to max out the RPM, 12,000. It's looking at about 12 thousandths inch per tooth at 600 inches per minute. So it maxed out inches per minute. It maxed out the spindle RPM on both the conservative and the aggressive. Okay, for a depth of cut of up to 1.5 inches and a step over of about 200 thousandths. So that is what, 20% or so? Maybe 20, 25% of the tool diameter. In the integrated version, you're going to have a slider between conservative and aggressive, and you're going to be able to look at the numbers and view how they change. Okay. In the integrated version, when you hit OK, it updates all of this data here for you. I'm going to go ahead and cancel that, come back in. So we're looking at only 550 inches per minute is what I input, which is, again, below the suggested value. The next thing you're going to do is come over to the roughing tab. Your first cut amount is going to be the max cut you want. And in this case, I'm going to allow it to do up to 1.5 inches. My flute length accommodates that, and at a 3/4 inch tool, that's going to be totally fine. My step over is 30%. That gets loaded in from the VoluMill options, which are here. So if you've never checked this out, everybody has this option. This is normally, pocket in, pocket out, zigzag. If you scroll down, you get VoluMill. And when you select VoluMill, you have this little extra box. You click on that, and you get the VoluMill specific options. Okay? So let's kind of go through these. Entry method. Now in 2017, we have 3 different entry methods. We can go through a pre-drilled hole, we can ramp in, or we can spiral in. That pre-drilled hole option is awesome. If you are using a tool that has, is not center cutting, choose that option, and it's going to allow you to come in through a pre-drilled hole. Ramp angle, if we are spiraling or ramping in, this is going to be the angle we do that in. The entry length, our floor clearance right now. So right now it's set to 10 thousandths. This would be, you would use a clearance. Actually, this clearance is pretty important. As the tool needs to move from one area of the pocket to the next, it's going to lift up a certain amount over the machined areas. That's what this clearance is. So it's not a bottom allowance. It's sort of like a clearance plane within the scope of the feature. We have our high feed rate, which is 600 inches per minute. At no point do I want this to move over 600 inches per minute as it's moving from sector to sector. And we have a full entry spiral option. This smoothing radius is one of the most important numbers that we can control. So what this is when we are avoiding sharp corners and we're actually going to curve those corners, this is the radius or the optimal radius we're going to be targeting. It's based on the tool diameter, and according to VoluMill, 45% is the optimal number. It's the most efficient number. Now, that number is going to change based on your part geometry. Okay, so I'll show in a later example here. As you reduce this number, it's going to allow the tool to reach into more areas. It's going to be a tighter radius, and so it's going to be able to reach tighter spots. But it also means that we should bump down the feeds and speeds. If it's a higher number, we're going to get a little bit rougher pass, but we can bump the speeds up. So there's a trade-off there that is going to be something that is dependent on the feature geometry. I'm going to keep this at 45 for this example. The next 2 checkboxes are pretty important as well. Side mill only. Essentially, what this means is, are we going to ever get into a situation where we are cutting basically a slot? And if we don't want that, we're going to check side mill only. Now, it will always give preference to that, but we can force it. And then lastly, avoid sharp corners for repositioning. I'll basically just have to show you an example of this. As the tool needs to get from one area to the next, in the past, it would always feed up to a clearance plane and then wrap it up to a rapid plane. And it would make those transitions. Once it rapids up to the plane and moves over an X and Y, that would be a sharp corner. And we're trying to avoid sharp corners. So this allows you to avoid those, and it will round that as it reaches the plane. Okay. Now this next section down here under the override section, it's overrides. If we want to force a step over amount, we can do that. If we want to force a max slot depth or a slot feed rate, we can do that as well. Okay. Now some of these don't become available if I have side mill checked only. Okay. So remember, side mill only, we're only going to do side milling. We're never going to get into a situation where we're cutting the full diameter of the tool. If we allow it to choose, Then we can override and tell it, if you are going a full slot cut, minimize the depth here or reduce the feed rate here. Okay, and you'll see that in the G code. And then lastly, we can override the entry parameters. We can override the entry RPM, and we can also create a dwell time between the entry and the actual cutting. So there's not a lot of data here, but there's enough to get a good toolpath. So let's take a quick look again. We've got a 3/4 inch 4-flute carbide. We're at 12,000 RPM, 550 inches per minute. Now, I'll tell you, if you don't believe that number, go to YouTube and just search VoluMill. Okay, we've got a lot of different people filming VoluMill toolpaths, and they're giving their cutting data, and you can watch the cutter. You don't have to try this on your own machine. You can watch it, you can hear it. It's beautiful. So I definitely recommend you go through and just search VoluMill and look up some examples. The cut time on this, less than 30 seconds. Less than 30 seconds. So we were at 4 minutes, 30 seconds, and we went down to about 30 seconds. So we're saving 4 minutes in total, but the percentage-wise is huge. And we're going to be set up for a finish pass just the same. All right. So I have a couple more options. That's in 2.5 axis. This is also 2.5 axis. This is a much larger part. I actually haven't run the numbers for this yet. So this is some sort of adapter plate for an LS7 motor. The overall size of this is massive. That distance there is 42 inches. Okay. And the amount of material we're removing is also massive. I went through and did the math. For all of these pockets and slots, we're removing about 60 cubic inches of aluminum. 60 cubic inches. Now, the way I did that was within SOLIDWORKS, I just created a quick feature that was all of the negative space. And then I used evaluate mass properties. And if you select all the bodies, you can get the mass properties, and the volume here is just about 60 cubic inches. So kind of a neat little trick if you're curious of how much volume you're actually cutting. Now, I was curious about that because some people judge your material removal rate based on volume. And so they target a volume removal rate tied to the, say, motor horsepower. So some numbers I've heard are about, let's say, 0.33 cubic inches per horsepower. So a good target number for a 10 horsepower motor would be about 33 cubic inches per minute. Okay. So what do we get here? I'm going to go ahead and let CAMWorks recalculate the toolpaths. So I have several features, and some of these features are actually groups of features, many features here. I have all of the rough mills combined into one. In this case, we're using a 1/2 inch 3-flute carbide tool, uncoated. The feeds and speeds data I came up with pretty similar to what we were using before, 12,000 RPM, 650 inches per minute in this case, which is, maybe we'll go more conservative. We'll adjust the feed per tooth here, and that brought that down to 450 inches a minute. Even I'm afraid to run the numbers that VoluMill gives me, but I don't have a lot of experience in front of a machine running these, so that's why I'm a little bit skeptical. And I truly believe everybody's going to be a little bit skeptical when they see these numbers. It's just one of those things that you really have to run for yourself on your machines to believe it. So we're at about 12 thousandths, 13 thousandths feed per tooth. On the passes, we're at 200% the tool diameter. These are very thin passes. And that's probably why I went ahead with the 650 inches per minute, because these passes, this cut is only, see if we can measure this guy. This cut's only 3/16 of an inch deep, so very shallow cut. We could definitely get away with the 650 number. Let's go 650. In the VoluMill parameters, this is what I want to show you. So notice I'm at that 45% smoothing radius. And in some of these areas, the tool is not actually cutting the full pocket. So in this case, here's the full pocket highlighted. Notice the tool is not cutting the entire slot. It can't fit. If I were to reduce that smoothing radius to, say, to 5, this would be on the very, very minimum low end. And preview this, we'll get it to recalculate. Notice we have toolpath in a lot more areas. And we have tighter corners. And in this case, it's coming through. Now, I would not run the tool like this. I probably would not recommend this, especially at that 650 number. We would have to bump it down quite a bit. But this kind of shows you what that number means. Okay? In areas like this pocket, where we have some tight corners over here on the bottom right-hand side, a smoothing radius of 45 might not reach all the way in, whereas a smoothing radius of maybe 20 or 25 might reach in and better prepare you for the finished pass. So pay attention to that. If you're not getting tool everywhere you want it, come in and adjust that smoothing radius. Notice another thing it's doing, as I kind of even this out here, notice there's very few rapid moves. It's actually feeding in a lot of different ways. And we have these curved tool paths as it curves up and it reaches that rapid plane and then curves back down. That is this avoid sharp corners for repositioning checkbox. If I uncheck that and allow sharp corners, we now see a lot more rapid moves. Now this might move faster if your rapid moves are significantly faster than your max feed rate, but it's going to be a little bit harder on your machine. So I really like the idea of this avoiding sharp corners. And lastly, this floor clearance of 0, you definitely should not do that. Give it at least 10 thousandths. Let's preview this guy. All right. And this 5% number is not very realistic either. Let's go back to the 45%. It's not going to cut all of the features. We will end up running a secondary roughing pass, probably with a conventional toolpath, but it's going to be much less material removed in that pass, and so the time we are spending in the conventional toolpath is much less than if we were to cut everything conventionally. All right, so let's take a look at this. We've got 8.5 minutes. 8.5 minutes. So I'm going to do the math here. We've got 60 cubic inches of material we're removing. We're doing it in 8.5 minutes. That's 7 cubic inches of material a minute. Okay. That gives you some perspective. Now, let's go and just for kicks, let's redo this as maybe like a pocket out toolpath. So let's change the pattern to a pocket out. First cut amount, I'm still just going to force it at 200. That's going to force it to do 1 depth of cut. We can get away with that. You know, it's only 3/16 of an inch. Step over. This is a tricky one because if I put too high of a number, then we're not going to get toolpath everywhere. So we'll stick with 40% right now. On the feeds and speeds, we probably are not going to be at 12,000 RPM at this point. We're probably going to be closer to, 7 to 8 to 9,000. So we'll maybe say 8,000. And the feed rate, a more realistic roughing feed rate, is probably going to be in the realm of 60 to 70 inches per minute. Now, if anybody disagrees with that, definitely type into the chat box or the questions box. If you want me to run it with certain numbers, I'm happy to do that. But I'm going to go ahead and we'll see what 70 inches per minute. That gives us a feed per tooth of about 3 thousandths. We could probably go up a little bit higher than that. Let's try 80 inches a minute. Or let's just force a feed per tooth of 4 thousandths. So at 96 inches a minute, let's go ahead and preview this. Looks like a little bit more conventional tool path. We're at 29 minutes, guys. 29 minutes. So that's about 2 cubic inches per minute, whereas the VoluMill was 7 cubic inches per minute. And remember, we're treating our tool better and we're treating our machine better at the same time. That's a no-brainer. So that's 2.5 axis. VoluMill is also available in 3 axis. So let's take a look at a 3-axis part. Now, all of the controls are pretty much the same. This part's a pretty cool part. It's a gear cover for a 6-axis robot. Maybe something you would probably cast, but if you're doing a prototype, you might get one machined. It's relatively large. The depth of this pocket is 4 inches, okay? And the overall size of this part is about 22 inches across. So it's a large part. We're going to remove a lot of material, and this is really where VoluMill shines. It really does. When we're chugging out material, it's the difference between cutting 10 parts a day and cutting 2 parts a day. So I did the same thing. I just have a basic 3-axis feature that's this entire part with a contain area set this way. And I've programmed it conventionally and through VoluMill. We'll take a look at the conventional toolpath first. See the top, we've got our sharp corners that we hate. This tool is a little bit different. It's a 3/4 inch carbide 3-flute. Okay, 3-flute tool. We can bump up this aluminum, I think, a little bit. Now, I'm concerned about, in this case, tool deflection, right? I've got a lot of stick out here. I'm trying to cut a 4-inch deep pocket. I'm going to have to be a little bit more conservative in my toolpaths no matter what. So what I have set here is 7,000 RPM, 45 inches a minute, 2 thousandths feed per tooth. Okay. We're taking multiple depths of cut, and they're all evenly spaced. Total time on this roughing, 63 minutes. 63 minutes. On the VoluMill, same tool, 3/4 inch 3-flute. We're at 12,000 RPM, 500 inches a minute. Let's bump that down. We're a little bit concerned about tool deflection. Let's go down 400 inches a minute. Now this is below the suggested number, okay? It's below it. Under the pattern, we're at 30% step over, max step over. And notice in 3-axis, the menu is the exact same. Okay, so 3-axis, 2.5 axis, all of the menus are the exact same. No extra training needed. And I should also say I reduced the cut depth on this. We could be taking 1.5-inch cut depth, and I have the cut depth at 3/4 of an inch. And I did that mostly out of concern for the tool deflection, the longer tool, okay? So we're probably doubling the amount over what you would normally do. And the cut time's about 12 or 11 and a half minutes. So we went from 63 minutes down to 11 and a half minutes. I'm going to go ahead and simulate this so you guys can kind of watch and see how this toolpath works. I'm going to slow it down a tiny bit. I want you to watch how it is always moving in either a spiral or some sort of circular pattern. Now this entryway is always going to simulate a little bit slower than the rest of it, and because there's a lot more moves within this. And as soon as it gets out of the entry, as it's spiraling down, it's going to go to depth. And once it gets there, then it's going to start roughing out. One of the cool things about this we'll see is it's going to go as deep as it can to rough out as much material as possible. And then you'll see it actually step up and hit some areas that it couldn't reach at the full depth. That's a more efficient way of cutting this. There's that full spiral entry. Notice if you watch closely, the radial depth of cut is constant as much as possible. That means the tool is going to have a certain load, a certain force on it. The motor is going to be running at a certain efficiency, and that's going to stay pretty much constant as it's spiraling through. See how it's chipping away at it? It's never fully engaged. And that right there is the reason why we can run these at higher spindle speeds and higher feed rates and actually get away with lower cutting forces. There's a lot of math that goes into figuring out this shape based on even the 2.5 axis shape, but imagine the 3 axis shape. There's a lot of math that goes into this, and that's why, a company like VoluMill has been working on this technology for 10 years, and they're still continuing to improve it. I think we're on VoluMill version 7.0 now. And with every new feature, we get better feeds and speeds calculator. We get more options as far as the entry into it and the movement from areas of the pockets to other areas. It's getting better and better. So that's about all I had for you guys during this webinar. I really wanted to give you an introduction to VoluMill, how it operates within CAMWorks, what sort of things to be thinking about when you start to investigate VoluMill or you start to use it. Where are you going to pull your feeds and speeds from? Where can you get some more information or some more, maybe some testimonials? It's very easy to use. And if you're chugging out a lot of material, it's going to pay for itself so quickly. I should also say we've been using aluminum in all of these cases, but in actuality, VoluMill works very, very well the harder the material it is. I'm going to go ahead and pause this. I'll leave this, if you want to write down that web address, that is where you would download the Milling Advisor. Again, I don't expect you to need to use this, come say Service Pack 1. But for right now, I would still recommend using this rather than the built-in, the new integrated feeds and speeds calculator. If you have any questions for me about CAMWorks and VoluMill or anything within CAMWorks, you can definitely shoot me an email. Love to hear from you guys. We have a lot of webinars online on our YouTube page, youtube.com/GoEngineer. We do these webinars basically monthly. I should say this link goes to our share file page, so I don't anticipate this link going down at any time. And if it does go down at any time, just shoot me an email and I can get this file to you guys. It's very hard to find now that it's been discontinued. So with that, thank you guys for watching, and I'll catch you next time.